25th of November, 1940, Hatfield Aerodrome just north of London. Jeffrey de Havilland Jr. climbed into the cockpit of a bright yellow aircraft that shouldn't exist. The Air Ministry had rejected it. Military experts had dismissed it. Senior RAF commanders called it a waste of time and resources. But there, it sat on the tarmac. A sleek twin-engine aircraft painted in brilliant yellow dope. An aircraft built almost entirely of wood in an age of metal. An aircraft with no defensive guns in a war where bombers bristled with turrets. An aircraft that would prove faster than the fighters trying to shoot it down. De Havilland Jr. ran through his pre-flight checks. 2 Rolls-Royce Merlin engines, the same engines that powered Spitfires and Hurricanes. But this aircraft was bigger, heavier. It carried 2 men instead of 1. It had a bomb bay, where a fighter had guns. Every calculation said it should be slower than a fighter. Every expert said it was impossible, but Jeffrey's father had built this aircraft on a radical premise. If you made it light enough and sleek enough, it wouldn't matter that it was bigger. It would still be fast. Faster than anything Germany could throw at it. The engines coughed to life. The propellers spun into invisible discs. De Havilland Jr. advanced the throttles. The Mosquito accelerated down the runway. It lifted off smoothly. And in that moment, everything changed. Within minutes of takeoff, the test pilot knew his father had been right. The aircraft handled beautifully, responsive, quick, powerful. Later that day, during high-speed runs, the Mosquito hit 388 miles per hour. That was faster than any bomber in existence. That was faster than most fighters. A wooden aircraft built by furniture makers had just become the fastest operational aircraft in Britain. The Germans would call it Der Mosquito. German pilots would fear it. German night fighters would chase it and fail to catch it. German flak gunners would aim at it and miss. The Mosquito would fly over Germany in broad daylight without escort and return home safely. It would drop bombs on Berlin while Goering gave a speech. It would photograph German defenses from altitudes where no fighter could reach. It would shoot down more enemy aircraft than it lost. And it would do all of this while being made of plywood, balsa, and birch. The wooden wonder. The aircraft Germany couldn't catch. The story of the Mosquito begins 3 years earlier, in late 1937. Jeffrey de Havilland, the founder of the de Havilland Aircraft Company, watched the European situation deteriorate. War was coming. Britain would need bombers. Lots of them. But the Air Ministry's current specification troubled de Havilland. They wanted heavy bombers with multiple defensive gun turrets, bombers that would fly in formation and fight their way to the target. De Havilland thought this was wrong, fundamentally wrong. Defensive guns added weight reduced speed, and speed was the best defense. De Havilland had experience with fast commercial aircraft. His company built the DH-91 Albatross, a sleek airliner with wooden construction. It was fast, it was efficient, and it gave de Havilland an idea. What if you took the Albatross concept and turned it into a bomber, a light, fast, unarmed bomber that relied on speed to survive? No turrets, no gunners, just 2 pilots and bombs. Make it aerodynamically clean. Make it powerful. Make it so fast that enemy fighters couldn't catch it. He presented the idea to the Air Ministry in September 1938. The reaction was dismissive. Air Marshal Wilfred Freeman listened politely, but most other officials laughed at the concept. A wooden bomber? In 1938? Aircraft were supposed to be metal. Everyone knew that. Wood was old-fashioned, obsolete. Besides, an unarmed bomber was suicide. German fighters would tear it apart. The proposal was rejected, but de Havilland didn't give up. He argued that wood had advantages. Britain had plenty of wood. The furniture industry could build wooden aircraft. That would free up aluminum and steel for other uses. Wood had an excellent strength-to-weight ratio, and wood was actually better than metal in some ways. It didn't fatigue like metal. It was easier to repair. Battle damage to wooden structures could be fixed in the field by carpenters. You needed specialized equipment to repair metal aircraft. The Air Ministry remained skeptical. They wanted bombers that could defend themselves. They wanted gun turrets, armor plating, multiple crew members to share the workload. De Havilland's proposal seemed reckless, dangerous. A wooden aircraft with no guns was a death sentence for its crew. The rejection stood. Then the war started. On the 1st of September, 1939, Germany invaded Poland. On the 3rd of September, Britain declared war. Suddenly, everything changed. Britain needed aircraft desperately. Not just a few, thousands. The factories couldn't build them fast enough. Aluminum supplies became critical. Every pound of aluminum was precious. And, most importantly, the early bomber operations revealed a harsh truth. Gun turrets didn't work. German fighters attacked from angles where the guns couldn't engage. Bombers were being shot down regardless of their defensive armament. De Havilland saw his opportunity. In October 1939, he revised his proposal. This time, he emphasized the wood construction angle. The aircraft wouldn't compete for aluminum supplies. It would use materials Britain had in abundance. The furniture industry, currently idle because of the war, could build the components. And, most importantly, the aircraft would be fast. Fast enough that German fighters couldn't catch it. Fast enough that it didn't need guns. The proposal reached Air Marshal Wilfred Freeman again. Freeman was one of the few senior officers who understood de Havilland's logic: speed over defense, performance over protection. Freeman authorized a contract for 50 aircraft on the 1st of January 1940, but there was a catch. The Air Ministry wanted proof. One prototype had to be built first. If it worked, production would continue. If it failed, the program would be canceled. De Havilland set to work immediately. His design team was small but talented. They had to solve problems that seemed impossible. How do you build a bomber from wood that's as strong as metal? How do you make wooden structures withstand the stresses of high-speed flight? How do you achieve a smooth aerodynamic surface with wood? The answers came from the company's experience with the Albatross airliner. The key innovation was the sandwich construction, 2 thin layers of birch plywood with a core of balsa wood in between. The result was incredibly light, yet remarkably strong. The plywood skins handled the tensile loads. The balsa core provided rigidity and prevented buckling. Adhesives bonded everything together. When properly constructed, this sandwich structure had a better strength-to-weight ratio than aluminum, and it was easier to shape into complex curves. The fuselage was built in 2 halves. Each half was constructed in a massive mold. The inner skin went in first, then balsa strips carefully positioned, then the outer skin. Everything was glued and clamped. After the adhesive cured, the 2 halves were joined along the center line. The result was a smooth, strong, lightweight fuselage with no external rivets or seams. It was aerodynamically perfect. The wings used similar construction but with different internal bracing. The main spar was a massive I-beam made of laminated wood. Secondary spars provided additional support. Ribs shaped the airfoil. The sandwich skins covered everything. The wings were attached to the fuselage with 4 large bolts. Simple, elegant, strong. The entire aircraft could be built by skilled carpenters with minimal metalworking equipment. But would it fly? That was the question nobody could answer until the prototype was complete. Construction took nearly a year, much longer than de Havilland had hoped. The war was intensifying. France fell in June 1940. The Battle of Britain raged through the summer. Britain desperately needed every aircraft it could get. And here was de Havilland, consuming Merlin engines and skilled labor to build an unproven wooden bomber that might not even work. Lord Beaverbrook, the Minister of Aircraft Production, was skeptical. He wanted proven designs in mass production, not experimental aircraft that might fail. He nearly canceled the Mosquito program in July 1940. De Havilland's general manager, L.C.L. Murray, made a desperate promise: 50 Mosquitoes by December 1941. If the company met that target, would Beaverbrook allow production to continue? Beaverbrook agreed, though he remained doubtful. The prototype was finally ready in November 1940. It looked stunning. The bright yellow paint made it visible from miles away. That was intentional. This was a test aircraft. It needed to be seen. But beyond the paint, the aircraft had beautiful lines, smooth, clean, fast-looking even when sitting still. The Merlins gave it power. The wooden construction gave it lightness. The aerodynamic design gave it efficiency. On paper, it should be very fast, but paper calculations can be wrong. Jeffrey de Havilland Jr. took it up on the 25th of November. The test flight revealed only minor issues. The aircraft handled well. The engines performed properly. The controls were responsive, and it was fast. much faster than expected. Follow-up tests confirmed the initial results. At 22,000 feet, the Mosquito reached 392 miles per hour. That was 30 miles per hour faster than a Spitfire Mark II at its best altitude. The Air Ministry was stunned. A wooden bomber was faster than their best fighter. The implications were staggering. If the Mosquito could maintain that speed advantage, German fighters couldn't catch it. It could fly in daylight without fighter escort. It could attack targets that were too dangerous for conventional bombers. And most importantly, it proved de Havilland's theory. Speed was the best defense. Testing continued through early 1941. The Mosquito was flown to RAF Boscombe Down for official trials. The results exceeded everyone's expectations. Not only was it fast, but it could carry a respectable bomb load, 4,000 pounds internally. That was more than early Lancasters could carry. The range was excellent, over 1,500 miles with a full bomb load. The service ceiling was high, 37,000 feet. German fighters couldn't operate effectively at that altitude. Production authorization came through. Multiple variants were ordered. Photo reconnaissance versions without bombs but with cameras. Bomber versions with enlarged bomb bays. Fighter versions with cannons and machine guns in the nose. The Mosquito's versatility was becoming apparent. The basic design was so sound that it could be adapted for multiple roles. This would become one of the aircraft's greatest strengths. The first operational Mosquito flew on the 17th of September, 1941. It was a photo reconnaissance variant. Flight Lieutenant Alistair Taylor flew from RAF Benson to photograph the French-Spanish border. He completed the mission without incident. No German fighters intercepted him. The Mosquito was too fast, too high. German radar detected him, but by the time fighters were scrambled, he was gone. More reconnaissance missions followed. The Mosquitoes photographed German positions along the Atlantic coast. They photographed U-boat facilities in Norway. They photographed German industrial targets deep in the Reich. The loss rate was negligible. German fighters occasionally gave chase, but they couldn't catch the wooden aircraft. Flak was a danger, but the Mosquitoes flew so high that most flak couldn't reach them. The reconnaissance Mosquitoes proved the basic concept worked. Bomber Mosquitoes entered service in May 1942. The first operational mission was on the 31st of May. 4 Mosquitoes from No. 105 Squadron attacked Cologne. They flew in daylight without escort. They dropped their bombs and returned safely. It was a small raid, symbolic rather than strategic, but it demonstrated that Mosquitoes could penetrate German airspace in daylight and survive. The bomber offensive expanded rapidly. Mosquitoes began flying regular missions over Germany. They attacked railway yards, factories, and military installations. They flew at medium altitude where accuracy was better than high-altitude bombing. They flew fast enough that German fighters struggled to intercept. The loss rate remained remarkably low. In 1942 and 1943, Mosquito bomber losses averaged less than 1% per sortie. That was exceptional. Lancasters and Halifaxes were losing over 3% per sortie during the same period. The secret to the Mosquito's success was its performance envelope. At altitude, it was faster than German fighters. German FW-190s and Bf-109 fighters could dive on Mosquitoes from above, but catching them in level flight was nearly impossible. The Mosquito pilot would see the fighters coming. He would advance the throttles to full power. The Merlins would roar. The Mosquito would accelerate. The German fighters would chase, but they couldn't close the distance. The Mosquito would pull away. At lower altitudes, the situation was more dangerous. German fighters were faster at sea level than in altitude, but Mosquito pilots learned to use their aircraft's strengths. The Mosquito could outclimb German fighters. When attacked at low level, the Mosquito pilot would go to full throttle and pitch up, climbing at over 2,000 feet per minute. The German fighter would try to follow, but the Mosquito would be gone, climbing into the sky where the Germans couldn't follow effectively. Night fighter Mosquitoes became some of the war's most successful aircraft. Equipped with airborne radar, they hunted German bombers over Britain. They hunted German night fighters over Germany. They flew intruder missions, prowling German airfields and shooting down aircraft as they tried to land. The Mosquito night fighter was fast enough to catch German bombers, maneuverable enough to dogfight, and armed with 4 20mm cannons and 4 machine guns. The firepower was devastating. One Mosquito night fighter became famous for its combat record, LR-503, known as F for Freddy. It flew with No. 109 Squadron and later No. 105 Squadron. It completed 213 operational sorties, more than any other Allied bomber in the entire war. It survived attacks by German fighters. It survived flak damage. It survived mechanical failures. F for Freddy seemed indestructible. It only crashed after the war ended during a publicity flight in Canada. Both crew members died, but the aircraft had proven the Mosquito's durability. The Mosquito's versatility led to specialized variants for special missions. One of the most famous was Operation Jericho, the raid on Amiens prison on the 18th of February, 1944. The prison held members of the French resistance. They were scheduled for execution. British intelligence requested a bombing raid to breach the prison walls and allow the prisoners to escape. It was an extraordinarily difficult mission. The target was small. Civilian buildings surrounded it. Precision was critical, and it was in occupied France, heavily defended. 3 Mosquito squadrons were assigned to the mission. Number 4, 6-4 Squadron Royal Australian Air Force, Number 4, 8-7 Squadron Royal New Zealand Air Force, and Number 21 Squadron RAF. 19 Mosquitoes in total, each carried 4 500-pound bombs. The plan was to attack in 3 waves. The first wave would breach the outer walls. The second wave would destroy the guard barracks. The third wave would blast open the prison buildings themselves. The attack required exceptional flying skill. The Mosquitoes had to fly at extremely low altitude to ensure accuracy. 50 feet off the ground in some cases, they had to identify the correct buildings and place bombs precisely. Any mistake would kill prisoners instead of freeing them. And they had to do this while German flak batteries shot at them and German fighters tried to intercept them. The raid was launched at noon. The Mosquitoes flew across the English Channel at wave-top height. They crossed into France and headed for Amiens. German radar detected them, but the low altitude made tracking difficult. The Mosquitoes arrived at the prison at 12 minutes past noon. The first wave attacked immediately. Bombs struck the outer walls. Explosions tore gaps in the masonry. Prisoners inside heard the blasts and realized what was happening. The second wave attacked the guard barracks. Bombs destroyed both buildings. German guards were killed or wounded. Confusion reigned. The third wave attacked the prison buildings themselves. More explosions, more breaches in the walls. Some bombs hit too accurately, killing prisoners. But most achieved their objective. The walls were breached. Prisoners could escape. Over 100 prisoners fled through the gaps. Not all escaped. Some were recaptured. Some were killed during the raid. But many made it to safety and rejoined the resistance. The mission cost 2 Mosquitoes shot down. One pilot, Group Captain Charles Pickard, was killed. Pickard was one of the RAF's most experienced Mosquito pilots. His loss was deeply felt, but the raid succeeded. It demonstrated the Mosquito's precision capabilities, and it showed that the Wooden Wonder could execute missions that no other aircraft could accomplish. The Mosquito's speed advantage persisted throughout the war. German aircraft designers tried to develop fighters fast enough to catch Mosquitoes. The FW-190D series had better high-altitude performance. The Me-262 jet fighter was much faster, but these aircraft arrived too late and in too few numbers. For most of the war, the Mosquito remained effectively uncatchable. German pilots reported frustration. They would spot a Mosquito, they would chase it, but they couldn't close the distance. The wooden bomber would simply accelerate away. The psychological impact on German forces was significant. Luftwaffe crews developed what they called Mosquito Schreck, Mosquito terror. They never knew when or where Mosquitoes might attack. The aircraft could appear anywhere at any time. Over Berlin in broad daylight, over airfields at night, over coastal installations at dawn. The Germans couldn't predict Mosquito operations. They couldn't effectively defend against them. The Mosquitoes attacked with impunity. Production of the Mosquito reached impressive numbers. Over 7,700 were built by the war's end. Multiple factories in Britain produced components. Canadian factories built complete aircraft. Even Australia manufactured Mosquitoes. The distributed production system worked well. The furniture industry's involvement meant skilled craftsmen were building aircraft instead of sitting idle. Women who had worked in furniture factories before the war now built wings and fuselages for Mosquitoes. The construction process was labor-intensive but efficient. Each fuselage took about 4,000 man-hours to build. That sounds like a lot. But consider that a Lancaster took over 18,000 man-hours. The Mosquito was faster to build despite being wooden. The modular construction helped. Sub-assemblies could be built in one location and transported to final assembly elsewhere. This distributed manufacturing reduced vulnerability to bombing. If one factory was destroyed, others continued producing. Quality control was critical. Wood construction required precision. The adhesives had to cure properly. The joints had to fit perfectly. Any weakness in the structure could be fatal. Inspectors checked every major assembly. They rejected components that didn't meet standards. The rejection rate was kept low through careful work, but quality was never sacrificed for speed. Crews depended on structural integrity. One failure could kill them. The Mosquito's operational record speaks for itself. Over 39,000 combat sorties were flown. Over 600,000 tons of bombs were dropped. Losses totaled around 400 aircraft in combat. That's a loss rate of roughly 1%. Compare that to Lancaster losses of over 3,000 aircraft out of over 150,000 sorties. The Lancaster loss rate was over 2%. The Mosquito was twice as likely to survive any given mission. Mosquito night fighters claimed over 600 enemy aircraft destroyed. Some pilots became aces flying Mosquitoes. They hunted German bombers and fighters in the darkness. Their radar allowed them to find targets invisible to the naked eye. Their speed let them catch fleeing aircraft. Their firepower destroyed targets with short bursts. The Mosquito night fighter was one of the most effective aircraft of the war. The versatility of the design allowed it to adapt to changing requirements. When Germany began launching V-1 flying bombs, Mosquitoes hunted them. The wooden fighters were fast enough to catch the pilotless bombs. They would fly alongside and tip them over with their wingtips, sending them crashing harmlessly into the sea. Other Mosquitoes carried rockets to attack German shipping. Still others carried marker flares to lead bomber streams to targets. The basic design accommodated all these modifications. After the war, the Mosquito's career continued. Some were converted to target tugs. Others became trainers. A few became executive transports. The type remained in service with some air forces into the 1950s, but the age of wooden aircraft was ending. Metal construction dominated. Jet engines replaced pistons. The Mosquito represented the pinnacle of piston-engine wooden aircraft design. Nothing that came after matched its combination of speed, versatility, and effectiveness. Jeffrey de Havilland's vision had been vindicated. Speed was the best defense. An unarmed bomber could survive if it was fast enough. Wood could compete with metal if properly engineered, and sometimes the experts were wrong. The Air Ministry had rejected the Mosquito concept. They had called it impractical, dangerous, a waste of resources. But Jeffrey de Havilland had built it anyway, and it became one of the most successful aircraft of the entire war. The hidden command that launched the Mosquito was Freeman's authorization on the 1st of January, 1940. It wasn't a dramatic order, it wasn't a famous directive, just a quiet authorization for one prototype and 50 production aircraft. But that decision changed the war. It gave Britain an aircraft that could attack Germany in daylight and return safely. It gave the RAF a reconnaissance platform that German fighters couldn't catch. It gave Bomber Command a precision bomber for special missions. And it gave night fighter squadrons a weapon that terrorized German bomber and fighter crews alike. The Mosquito proved that unconventional thinking could solve seemingly impossible problems. Britain needed bombers but lacked aluminum. Solution? Build them from wood. Britain needed speed, but conventional wisdom said bombers had to be slow. Solution? Remove the guns and rely on performance. Every expert said it wouldn't work. Every calculation said it was impossible. But Jeffrey de Havilland ignored the experts. He trusted his engineering instincts, and he created an aircraft that Germany couldn't catch. The wooden wonder, the Mosquito, Britain's fastest bomber and one of its most successful fighters, all because someone dared to think differently. The technical achievement of the Mosquito becomes even more remarkable when you understand what de Havilland's engineers accomplished with wood. Modern aircraft builders look at the Mosquito and shake their heads in disbelief. Building an airframe from plywood that can handle 400 miles per hour requires solving problems that seem impossible. Wood warps, wood splits, wood absorbs moisture. Any of these issues at high speed could be catastrophic. The de Havilland team solved them all. The adhesive was critical. Early aircraft using wood construction often failed because the glue joints separated under stress. De Havilland's engineers tested dozens of adhesive formulations. They needed something that would remain strong in freezing temperatures at altitude, something that wouldn't break down from fuel or oil exposure, something that wouldn't weaken in humid conditions. They settled on a casein-based adhesive called aerolite. It bonded wood better than any previous glue. More importantly, it remained strong across extreme temperature ranges. The curing process required precise control. The adhesive had to cure at specific temperatures and pressures. Too hot and the wood would char. Too cold and the adhesive wouldn't set properly. De Havilland built enormous autoclaves where fuselage halves could cure under controlled conditions. Temperature was monitored constantly. Pressure was maintained precisely. Workers learned to recognize the signs of proper curing. A properly cured fuselage half had a distinctive appearance and feel. Experienced workers could tell by sight whether the bonding was correct. The wood itself came from carefully selected sources. The birch plywood came from Canada and Scotland. Only certain grades were acceptable. The wood had to be free of knots and defects. The grain had to run in specific directions. Each sheet was inspected before use. Rejected sheets went to less critical applications. The balsa came from Ecuador. It was light but strong when used correctly. However, balsa quality varied significantly. Workers had to sort through shipments to find pieces suitable for aircraft construction. Moisture control was a constant concern. Wood expands when it absorbs moisture and contracts when it dries. In an aircraft flying at high speed, even small dimensional changes could cause problems. The solution was to seal the wood completely. Multiple coats of dope covered every surface. The dope created a waterproof barrier. It also added stiffness to the structure. The bright yellow paint on the prototype wasn't just for visibility. It was the final layer of a protective system that kept moisture out. The manufacturing process required skills the traditional aircraft factories didn't have. De Havilland recruited from the furniture industry. Cabinet makers who had spent decades working with wood now built aircraft. Their experience with joints and adhesives translated perfectly to aircraft construction. They understood how wood behaves under stress. They knew how to achieve tight tolerances with hand tools. These craftsmen became the backbone of Mosquito production. Training took time. A skilled furniture maker couldn't simply walk into a factory and start building Mosquitos. They needed to learn aircraft construction standards. They needed to understand stress analysis. They needed to master the specific techniques required for aircraft structures. De Havilland established training schools. New workers spent weeks learning before they touched actual aircraft components. The investment in training paid off in quality. Mosquito structures rarely failed due to manufacturing defects. Women played a huge role in Mosquito production. Many had worked in furniture factories before the war. When the men left for military service, the women took over. They proved just as capable as their male colleagues. They learned to read complex engineering drawings. They mastered precise assembly techniques. They worked long shifts in sometimes difficult conditions. Their contribution was essential to meeting production targets. The wing construction deserves special attention. Aircraft wings must withstand enormous loads. They support the entire weight of the aircraft plus flight loads that can multiply that weight many times over. Traditional metal wings use internal bracing and external skin to handle these stresses. The Mosquito's wooden wings had to achieve the same strength with completely different materials and construction methods. The main spar ran the length of the wing. It was a massive wooden I-beam made from layers of spruce laminated together. The web of the I-beam was over 6 inches deep in places. The flanges were built up from multiple layers bonded and clamped. When complete, the spar could handle loads exceeding 20,000 pounds without failure. It was a masterpiece of wooden engineering. The wing skin used the sandwich construction throughout, inner and outer plywood layers with balsa core, but the thickness varied across the wing. At the root, where loads were highest, the skins were thickest. Toward the tips where loads decreased, the skins became thinner. This tapering saved weight while maintaining strength. Getting it right required detailed stress calculations. De Havilland's engineers performed these calculations by hand. No computers existed to check their work. They had to be right the first time. The engine installation presented unique challenges. The Merlin engines produced tremendous heat. That heat had to be managed carefully. In a metal aircraft, heat dissipates through metal structures. Wood doesn't conduct heat as effectively. The engine nacelles used a combination of wood and metal. The parts closest to the engines were metal. The outer cowlings were wood. Cooling air flowed through carefully designed passages. The system worked, but it required extensive testing to get right. The propellers themselves were an engineering challenge. The Mosquito used large three-bladed propellers. Each blade was over 11 feet long. At cruise speed, the propeller tips moved at supersonic velocity. The propeller design had to account for compressibility effects that weren't well understood in 1940. De Havilland worked with propeller specialists to develop the optimal design. The result was a propeller that operated efficiently across the Mosquito's speed range. Fuel capacity was generous. The wings contained self-sealing fuel tanks. Total capacity exceeded 1,200 gallons. That gave the Mosquito its excellent range. Self-sealing tanks were critical for survival. When punctured by bullets or shrapnel, the tank liner would swell and seal the hole. This prevented fuel from leaking. Many aircraft survived attacks because their self-sealing tanks kept them flying long enough to reach safety. The cockpit design prioritized visibility and ergonomics. The pilot and navigator sat side by side under a large canopy. The forward view was excellent. The pilot could see almost straight down past his feet. This visibility was crucial for low-altitude operations. The navigator needed to see landmarks for visual navigation. Both crew members needed to watch for enemy fighters. The greenhouse canopy provided that visibility. Instruments and controls were arranged logically. The pilot had full control of the aircraft from the left seat. Throttles, mixture controls, propeller pitch controls, all within easy reach. The navigator had a small desk with maps and navigation instruments. Communication between pilot and navigator was via intercom. In combat, clear communication could mean the difference between survival and death. The bomb bay was remarkably versatile. Early versions could carry 4 500-pound bombs internally. Later versions had strengthened structures that allowed a single 4,000-pound bomb. That 4,000-pound bomb was called a cookie. It was a cylinder filled with explosive. When dropped from altitude, it created devastating blast effects. Mosquitoes carrying cookies attacked German cities with precision that heavy bombers couldn't match. Photo reconnaissance Mosquitoes carried cameras instead of bombs. The cameras were mounted vertically in the bomb bay. They could photograph the ground from high altitude with remarkable resolution. The images revealed details that analysts used to plan bombing raids. Bridges, factories, railways, even individual vehicles could be identified. The Germans knew they were being photographed, but couldn't stop it. The reconnaissance Mosquitoes were simply too fast and flew too high. Fighter-bomber variants carried weapons externally as well as internally. Rockets could be mounted under the wings. These rockets were devastating against German shipping and ground targets. A salvo of 8 rockets delivered as much explosive power as a broadside from a cruiser. Mosquitoes attacked German ships in Norwegian fjords with these rockets. They sank or damaged dozens of vessels that would otherwise have threatened Allied convoys. The offensive armament on night fighter Mosquitoes was fearsome. 4 20mm Hispano cannons in the lower nose, 4 .303 caliber Browning machine guns above them. When all 8 weapons fired together, the effect was devastating. A 1-second burst delivered enough explosive and armor-piercing rounds to destroy most aircraft. Mosquito pilots learned to fire short bursts. Ammunition was limited, and every round had to count. The airborne radar in night fighters was revolutionary technology. The radar could detect other aircraft at several miles range. The operator, usually the navigator, would guide the pilot toward the target. As they closed, the radar screen would show the target's position. The pilot would maneuver until visual contact was made. Then he would close to point-blank range and open fire. Many German bomber crews never knew they were being tracked until the cannons opened up. Mosquito pilots developed signature tactics. When bouncing German bombers, they would approach from below and behind. This was the bomber's blind spot. Most German bombers had weak or non-existent ventral defensive armament. The Mosquito would slide underneath, barely 100 feet below. The pilot would pull up slightly, aim carefully, and fire. The German bomber would explode or catch fire. The Mosquito would break away and look for the next target. Some pilots claimed multiple kills in a single night using these tactics. Intruder missions were particularly dangerous. Mosquitoes would fly to German airfields and patrol nearby. When German night fighters tried to land, the Mosquitoes would attack. The German aircraft were slow and vulnerable during landing. Their landing lights made them easy targets. The Mosquitoes would shoot them down on approach or strafe them on the runway. This forced German night fighters to land quickly with minimal lights. Many crashed as a result. The Mosquito intruders created a climate of fear around German airfields. The loss of F for Freddy after the war ended was particularly tragic. The aircraft had survived 213 combat missions. It had flown over Germany repeatedly. It had been shot at by flak. It had been chased by fighters. It had suffered mechanical problems. But it always returned. Then, on the 10th of May, 1945, just 2 days after the war in Europe ended, it crashed at Calgary Airport. The pilot, Flight Lieutenant Maurice Briggs, and his navigator died. They had survived the war only to die in a peacetime accident. F for Freddy was scrapped. Its combat record could never be duplicated. The Mosquito's success influenced post-war aircraft design. The concept of the fast, unarmed bomber proved valid. Speed was better defense than guns. This principle guided the design of bombers like the English Electric Canberra and later jet bombers. The idea that you could rely on performance instead of defensive armament became accepted wisdom. The Mosquito had proven it worked. The wooden construction didn't survive into the jet age. Metal was simply better suited to jet aircraft. The higher speeds and temperatures of jet flight exceeded wood's capabilities. But the engineering lessons learned from the Mosquito remained valuable. Sandwich construction techniques were applied to composite materials decades later. The same principles that made the Mosquito strong and light now make modern composite aircraft possible. Individual pilots and crews made the Mosquito legendary. These men flew into extreme danger night after night. They relied on their aircraft's speed and their own skill to survive. Some became famous. Others remained unknown outside their squadrons, but all of them shared common traits: courage, determination, skill, and absolute confidence in their wooden aircraft. Wing Commander Bob Bram was one of the most successful night fighter pilots. Flying Mosquitoes, he claimed 29 enemy aircraft destroyed. He developed tactics that other pilots copied. His aggressive flying style made him feared by German bomber crews. He was eventually shot down over Denmark and spent the rest of the war as a prisoner. But his record in the Mosquito remained unsurpassed. Squadron leader Brance Burbridge claimed 21 enemy aircraft destroyed in Mosquitoes. All of these were at night. He flew with navigator Bill Skelton. The two men developed an almost telepathic understanding. Skelton would guide Burbridge onto targets using the radar. Burbridge would execute the attacks. They became one of the war's most successful teams. Both survived the war. The Pathfinder force used Mosquitoes extensively. The Pathfinders flew ahead of bomber streams and marked targets with flares. This allowed the main force to bomb accurately, even through clouds. Mosquitoes were ideal for this role. They could reach the target first. They could mark it precisely. And they could escape before German fighters arrived in force. Pathfinder Mosquito crews had one of the most dangerous jobs in bomber command. They flew first and drew the initial defensive fire. Losses were high, but the men kept flying because the job had to be done. Weather reconnaissance Mosquitoes flew missions that seem almost suicidal. They would fly out over the Atlantic to gather weather data. This data was crucial for planning bomber operations, but the flights were dangerous. Bad weather could force an aircraft down into the ocean. Navigation errors could leave a crew lost with insufficient fuel to return. Many weather reconnaissance crews were lost without trace, but the survivors provided information that saved countless lives by allowing operations to be planned around weather conditions. The versatility of the Mosquito meant pilots needed diverse skills. A bomber pilot had to master low-level navigation and precision bombing. A night fighter pilot had to learn radar operation and night combat tactics. A reconnaissance pilot had to navigate alone over enemy territory and return with photographs despite intense opposition. Training programs evolved to teach these specialized skills, but fundamentally, all Mosquito pilots shared one requirement: they had to be good. The aircraft was demanding. It required precise handling. It rewarded skill and punished mistakes. The nickname Wooden Wonder became universally recognized. It captured everything the Mosquito represented: made of wood when aircraft were supposed to be metal, fast when it was supposed to be slow, successful when it was supposed to fail. The Germans had their own names for it. Der Mosquito was the most common, but German pilots also called it Teufelsapparat, the devil's device. That name revealed their fear and respect. The aircraft that appeared without warning and disappeared before they could respond. The bomber that attacked in daylight and escaped untouched. The fighter that hunted them in their own skies. German intelligence tried desperately to understand the Mosquito's secrets. They captured damaged aircraft. They interrogated crews who were shot down. They analyzed wreckage. They discovered it was made of wood and were astonished. Wood? In 1944? How was that possible? They tried to copy the design, but they lacked the manufacturing expertise. German industry had committed to metal aircraft. They had few skilled woodworkers. Their adhesives weren't as good as aerolite. Their attempts to build wooden aircraft never matched the Mosquito. The post-war years were difficult for surviving Mosquitoes. They were outdated almost immediately. Jets were faster. Jets flew higher. Jets were the future. The wooden bombers and fighters that had seemed so advanced in 1944 were obsolete by 1950. Most were scrapped. The wood was burned or left to rot. Of the 7,700 Mosquitoes built, fewer than 40 survive today. Most are in museums. Only a handful are airworthy. Each flying Mosquito is precious. They represent a technology that will never return. When a Mosquito flies today at an air show, crowds gather to watch. The sound of two Merlins at full throttle is unforgettable. The aircraft moves with speed and grace that seems impossible for something made of wood. Watching it, you understand why German pilots feared it, why British crews loved it, why it became legendary. The Mosquito represents a moment when everything came together perfectly. The right design, the right materials, the right performance, the right aircraft at the right time. The men who designed it are long gone. Jeffrey de Havilland died in 1965. His son, the test pilot, died in 1946 in a jet aircraft accident. The engineers who solved the technical problems have passed away. The workers who built the aircraft in factories and workshops across Britain are gone. The pilots and navigators who flew combat missions are mostly gone as well. Each year, fewer remain. Soon, there will be none. But the aircraft survives in museums and in memory. The hidden command that launched the Mosquito was Wilfred Freeman's quiet authorization in January 1940. Freeman understood what de Havilland was trying to achieve. He saw past the conventional wisdom that said wooden bombers were obsolete. He took a chance on an unproven design. That chance changed the war. The Mosquito gave Britain capabilities it desperately needed: fast reconnaissance, precision bombing, effective night fighting. The aircraft exceeded every expectation. Freeman's decision demonstrated something important about innovation. Sometimes you have to ignore the experts. Sometimes you have to try ideas that seem crazy. Sometimes you have to trust the iconoclasts who see solutions others miss. Freeman did that. He gave de Havilland the opportunity to prove his concept, and de Havilland delivered an aircraft that transformed aerial warfare. The story of the Mosquito is ultimately about people who refuse to accept limitations. De Havilland refused to accept that bombers had to be slow. His engineers refused to accept that wood couldn't compete with metal. The workers refused to accept that peacetime skills couldn't translate to wartime production. The pilots refused to accept that unarmed bombers couldn't survive. They all proved the doubters wrong. They created something extraordinary from ordinary materials. They built the aircraft Germany couldn't catch. The wooden wonder, the Mosquito, Britain's answer to those who said it couldn't be done. The Mosquito's operational history reveals patterns that illuminate the nature of air combat in the Second World War. Early operations in 1942 focused on proving the concept. Small raids, carefully selected targets, routes planned to minimize exposure to defenses. The goal was to demonstrate that unarmed bombers could survive. The early missions succeeded beyond expectations. Not a single Mosquito was lost to enemy fighters in the first 6 months of operations. Flak claimed a few aircraft. Mechanical failures caused others to crash, but German fighters couldn't catch them. This success emboldened mission planners. If Mosquitoes could fly to Cologne and back unscathed, what else could they do? The answer was nearly anything. By late 1942, Mosquitoes were ranging across occupied Europe. They photographed targets. They bombed factories. They attacked shipping. The loss rate remained remarkably low. Mosquito crews developed confidence bordering on invincibility. That confidence was mostly justified. Berlin became a particular focus. The German capital was heavily defended. Hundreds of flak batteries surrounded the city. Multiple fighter bases protected it. Most bomber raids on Berlin suffered heavy losses. But mosquitoes could attack Berlin in daylight and survive. The psychological impact on German morale was significant. If British bombers could reach Berlin in broad daylight, nowhere in Germany was safe. The attacks didn't cause massive physical damage. Each Mosquito carried relatively few bombs. But the message was clear. Britain could strike anywhere, anytime. One particular raid became famous. On the 30th of January, 1943, the Nazis held a massive rally in Berlin. It was the 10th anniversary of Hitler's rise to power. Goering was scheduled to speak at 11 in the morning. British intelligence knew about the rally. Someone decided mosquitoes should provide a counterpoint. 3 Mosquitoes from No. 105 Squadron were dispatched to Berlin. They arrived over the city precisely as Goering began speaking. The Mosquitoes dropped their bombs and escaped before German fighters could respond. Goering's speech was interrupted by air raid sirens and explosions. He was furious. The humiliation was complete. British wooden bombers had attacked Berlin in daylight during a major Nazi celebration. The raid was repeated on the anniversary of Hitler's speech in Munich. Every time the Nazis planned a major public event, mosquitoes appeared overhead. The Germans couldn't stop them. The sophisticated air defense system that protected Berlin was useless against aircraft that flew higher and faster than anything Germany possessed. The raids became known as spite raids, not designed to cause military damage, designed to embarrass and demoralize. They succeeded brilliantly. The Light Night Striking Force was formed specifically to use mosquitoes against Germany. This unit conducted what became known as nuisance raids. Small numbers of mosquitoes would attack German cities every night. The physical damage was limited, but the psychological impact was enormous. German workers couldn't sleep. Air raid sirens disrupted their rest constantly. The attacks came from different directions, at different times, against different targets. The Germans never knew where the next attack would occur. They had to man defenses constantly. Workers were exhausted. Production suffered. The genius of the nuisance raids was their efficiency. A handful of mosquitoes kept entire German cities on alert. Thousands of German soldiers manned flak batteries night after night. German night fighters flew constant patrols. All of this absorbed resources that could have been used elsewhere. And the mosquitoes kept coming. Night after night, month after month, year after year. The campaign continued until Germany surrendered. The mosquitoes' role in the V-weapon campaign was critical. When Germany began launching V-1 flying bombs against Britain, mosquitoes were assigned to destroy launch sites. These sites were small, well camouflaged, heavily defended. Conventional bombing was ineffective, but mosquitoes could attack with precision. They would approach at low altitude. They would identify the target. They would place bombs exactly where needed. The Air Ministry calculated that mosquitoes destroyed V-1 sites 5 times more efficiently than conventional bombers. It took 40 tons of bombs delivered by mosquitoes to destroy a site. It took 165 tons delivered by B-17s. The difference was accuracy. When V-2 rockets began falling on London, mosquitoes attacked the production facilities. The V-2 was manufactured at an underground factory in the Harz Mountains. The factory itself was invulnerable to bombing, but the supporting infrastructure wasn't. Mosquitoes attacked the railways bringing components to the factory. They attacked the electrical substations powering it. They attacked the administrative buildings coordinating production. Each attack was small, precise, devastating. Collectively, these attacks significantly disrupted V-2 production. The Mosquito service with the Pathfinder Force deserves extended discussion. The Pathfinders were formed to improve bombing accuracy. They would mark targets with colored flares. The main bomber force would bomb the markers. Simple concept, but difficult execution. The Pathfinders had to arrive first. They had to mark the correct target. They had to remain over the target long enough to ensure the main force saw the markers, all while being shot at by every German gun and fighter in the area. Mosquitoes were ideal Pathfinder aircraft. They could fly ahead of the bomber stream. They could mark targets from higher altitude than heavier bombers could reach. They could escape before German defenses concentrated. The combination of speed and altitude made them difficult to shoot down. Pathfinder Mosquito crews had elite status within Bomber Command. They were among the most experienced and skilled airmen. They flew the most dangerous missions. They had the highest loss rates, but they enabled the entire strategic bombing campaign to function effectively. Target marking evolved into a complex art. Different colored flares identified different aiming points. Green flares might mark the initial point, red flares the actual target. Yellow flares back up aiming points if the primary was obscured. The Pathfinder aircraft would circle the target. They would observe the bombing. If the markers were hit and destroyed, they would drop more. If the main force was bombing inaccurately, they would drop correction markers. The entire process required split-second timing and ice-cold courage. One mistake, and thousands of tons of bombs would hit the wrong target. Oboe was a radio navigation system that revolutionized precision bombing. Ground stations would send radio signals. Aircraft would receive these signals and use them to navigate precisely. Oboe could guide an aircraft to within a few hundred yards of a target, even through solid cloud cover. The system had limitations. It could only control one aircraft at a time. The range was limited by radio line of sight. But within its limitations, Oboe was devastatingly accurate. Mosquitoes equipped with Oboe became the most precise bombers in the world. Mosquito-Oboe combinations attacked German industrial targets with unprecedented accuracy. Oil refineries were hit repeatedly. Chemical plants were destroyed. Power stations were disabled. Each attack was small, sometimes just a few mosquitoes, but the cumulative impact was enormous. German industry couldn't function when key installations were repeatedly knocked out. Repair crews would fix the damage. Mosquitoes would return and destroy it again. This cycle continued throughout 1944 and into 1945. The cost of these operations in human terms was significant. Pathfinder crews flew 30 missions to complete a tour, but the loss rate was higher than for regular bomber crews. Many Pathfinder airmen didn't survive their first tour. Those who did were often asked to volunteer for a second tour. Some flew 80 or even 100 missions. The psychological strain was immense. These men knew the statistics. They knew their chances, but they kept flying because someone had to do it. Individual Mosquito squadrons developed distinctive identities. Number 105 Squadron specialized in precision bombing. Number 109 Squadron focused on night fighting. Number 139 Squadron became the premier reconnaissance unit. Each squadron had its traditions, its rivalries, its heroes. Squadron members formed bonds that lasted lifetimes. They had shared experiences that no one else could understand. They had faced death together repeatedly. That creates connections that don't fade. The ground crews deserve recognition for their essential role. Each Mosquito required extensive maintenance between missions. Engines needed servicing, airframes needed inspection, systems needed checking. The ground crews worked through the night to prepare aircraft for the next day's operations. They worked in all weather. They worked without recognition or glory, but the air crews trusted them absolutely. A properly maintained aircraft was the difference between survival and death. The Mosquito's wooden construction created unique maintenance challenges. Wood swells and shrinks with humidity changes. The adhesive joints had to be monitored for separation. Battle damage to wood structures required specialized repair techniques. Ground crews learned these techniques through experience. They became expert at assessing damage and determining whether an aircraft was safe to fly. Their judgment saved lives. An aircraft declared unserviceable stayed grounded. One cleared for flight went back into combat. The responsibility was enormous. Engine maintenance was particularly critical. The Merlin engines were reliable but required constant attention. Oil had to be changed regularly. Spark plugs needed replacement. Coolant systems required monitoring. Each engine had hundreds of parts that could fail. The ground crews knew every system intimately. They could diagnose problems by sound. An experienced mechanic could hear an engine running and know if something was wrong. This expertise was built through years of experience. You couldn't teach it in a classroom. You learned it by doing. The war's end came suddenly for many Mosquito units. Germany surrendered on the 8th of May, 1945. Squadrons that had been flying combat missions the day before suddenly had nothing to do. The transition was jarring. Men who had lived with constant danger now faced peace. Some adapted easily, others struggled. The bonds forged in combat didn't translate well to peacetime. Veterans found that civilians couldn't understand what they had experienced. The gap between their war experiences and civilian life seemed unbridgeable. Some Mosquitoes continued flying after the European War ended. The war against Japan continued until August 1945. Mosquitoes serving in the Far East flew missions against Japanese targets. The aircraft performed well in tropical conditions despite concerns about wood construction in humid climates. The protective dope coatings kept moisture out. The structure remained sound. Mosquitoes in the Pacific Theater proved as effective as those in Europe. The end of the war meant the end of production. The last Mosquito rolled off the assembly line in November 1950. Over 7,700 had been built. Production facilities were converted to other uses or closed. The workers who had built Mosquitoes returned to peacetime occupations. The furniture makers went back to making furniture. The women who had worked in factories returned home or found other employment. An entire industry disappeared almost overnight. The British government sold surplus Mosquitoes to various countries. Turkey bought some, Sweden bought others. Norway, Belgium, and several other nations acquired small numbers. These aircraft served for years after the war, some as target tugs, some as trainers, some as transports. The Mosquito's versatility extended into peacetime, but their days were numbered. Jets were faster and more capable. Propeller aircraft were obsolete. By the mid-1950s, most Mosquitoes had been scrapped. The preservation movement began in the 1960s. Aviation enthusiasts recognized that the Mosquito was disappearing. They located surviving aircraft and began restoration efforts. The work was difficult. Wood structures had deteriorated after decades of exposure. Many aircraft were incomplete wrecks, but dedicated volunteers persevered. They hunted for parts. They learned forgotten construction techniques. They rebuilt Mosquitoes piece by piece. Today's surviving aircraft exist because of their efforts. The emotional connection to the Mosquito remains strong among veterans. Pilots who flew it remember the aircraft fondly. They describe its handling characteristics with enthusiasm. They recall how it responded to control inputs, how it accelerated when the throttles advanced, how it climbed away from danger. For these men, the Mosquito wasn't just a machine. It was the aircraft that brought them home. That kept them alive through impossible missions. That gave them a chance when no other aircraft could. Navigators remember differently. They recall the cramped workspace, the hours spent calculating positions, the stress of guiding their pilot through darkness over hostile territory. They remember the satisfaction when they navigated perfectly and arrived exactly where they intended. They remember the fear when they made mistakes. But above all, they remember the partnership with their pilot, the absolute dependence on each other, the trust that developed over dozens of missions. Ground crew members remember the aircraft with professional pride. They built them or maintained them to the highest standards. They sent them off on missions knowing their work had to be perfect. When an aircraft returned damaged, they repaired it and sent it back out. When an aircraft didn't return, they felt the loss personally. That had been their aircraft, their crew. They remember feeling responsible, proud when things went well, devastated when they didn't. The legacy of the Mosquito extends beyond its combat record. It demonstrated that unconventional approaches can solve difficult problems. When everyone said metal was the only option, de Havilland used wood. When everyone said bombers needed defensive guns, de Havilland relied on speed. When everyone said it wouldn't work, de Havilland proved them wrong. This willingness to challenge conventional wisdom changed aviation. It showed that established solutions aren't always best. Sometimes you have to think differently. The technical lessons from the Mosquito influenced post-war aircraft design. The emphasis on aerodynamic cleanliness became standard practice. The concept of relying on performance rather than defensive armament shaped jet bomber design. The use of composite materials in modern aircraft traces back to lessons learned with wooden construction. Engineers studying the Mosquito decades later found principles that remained valid even in the jet age. The human lessons are equally important. The Mosquito's success depended on people. Jeffrey de Havilland's vision, Wilfred Freeman's support, the workers who built the aircraft, the crews who flew them, each played an essential role. Remove any one element and the story changes. The Mosquito succeeded because everyone involved was committed to making it work. They faced skepticism and opposition. They overcame technical challenges that seemed insurmountable. They persevered through setbacks and losses. Their collective effort created something remarkable. Today, when we look at a preserved Mosquito in a museum, we're looking at more than an artifact. We're looking at evidence of what can be achieved when talented people work toward a common goal. We're seeing the result of engineering genius combined with manufacturing skill and operational courage. We're witnessing the physical manifestation of determination and innovation. The wooden airframe might seem fragile, but it carried men through the most dangerous skies of the war. It performed missions that no other aircraft could accomplish. It proved that sometimes the impossible is just difficult. The hidden command that launched the Mosquito was just a few words on paper. Authorization to proceed with one prototype. Permission to use scarce resources on an unproven concept. Freeman signed that authorization knowing it might fail, knowing he might be criticized for wasting resources. But he believed in de Havilland's vision. He understood that innovation requires taking chances, that sometimes you have to trust the people who see possibilities others miss. His decision to sign that authorization changed history. It gave Britain a weapon that Germany couldn't counter. It demonstrated that British innovation could match German technology. It proved that sometimes the simplest solutions are the best. Build it light. Make it fast. Let performance be the defense. The Mosquito embodied these principles perfectly, and in doing so, it became one of the war's most successful aircraft, the wooden wonder that Germany couldn't catch. The Mosquito story reminds us that the best weapon isn't always the most complex or expensive. Sometimes it's the one that gets the job done reliably. The Germans built the Me-262 jet fighter. It was faster than the Mosquito, more advanced, more expensive, but it arrived too late and in too few numbers. The Mosquito was available when needed. It flew thousands of missions while the Me-262 was still in development. Availability beats sophistication when the war is being fought now. This principle applies beyond aviation. Military history is filled with examples of simple, effective weapons defeating complex, sophisticated ones. The Mosquito exemplified this perfectly. Take proven engines, build a clean airframe around them, minimize weight, maximize performance. The result was an aircraft that exceeded expectations precisely because those expectations were realistic. De Havilland didn't promise miracles. He promised a fast bomber that would work. He delivered exactly that. And in delivering, he created something that seemed miraculous. The men who flew Mosquitoes into combat trusted their aircraft completely. That trust was built through experience. The aircraft performed as advertised. It was fast. It was reliable. It brought them home. Veterans speak of their Mosquitoes with affection that seems almost inappropriate for a machine. But to them, it wasn't just a machine. It was a partner. It shared their dangers. It responded to their skill. It earned their respect mission after mission. That relationship between man and machine defined their war experience. When the last Mosquito veterans pass away, living memory of the aircraft will disappear. Future generations will see it only in museums and photographs. They'll read the statistics and learn the history, but they won't feel the vibration of twin Merlins at full power. They won't experience the surge of acceleration as the throttles advance. They won't know the relief of crossing the English coast after hours over enemy territory. They won't understand what it meant to fly an aircraft that could outrun anything chasing it. These experiences will become history rather than memory, but the aircraft itself will endure as testament to what was achieved when brilliant design met desperate necessity.